All right, so today, guys, we're going to talk about thermochemistry. And the first thing I wanted to touch on, which I think is quite humorous, is when you look at Fahrenheit versus Celsius versus Kelvin. So the Fahrenheit system is pretty much set up around human comfort, if you think about it. And it's really set up based upon mercury, but essentially, if it's 0 degrees Fahrenheit, it's just really cold outside. It's 100 degrees Fahrenheit, it's just really hot. And living here in Nebraska, we have a couple days every year that are above 100 Fahrenheit and a couple days every year that are around 0 Fahrenheit. But nothing too serious happens. Now, with Celsius, though, 0 degrees is just fairly cold because 0 degrees Celsius is 32 Fahrenheit. So we have, today actually being November 11th will actually be fairly cold. But 100 degrees Celsius is boiling point of water. You will be dead. Game over. So Celsius is kind of a scale based upon water, where we have freezing point of water is 0, 100, and then boiling point of water is 100, and then the increments go between that. The Kelvin scale uses molecular motion. So at 0 degrees Kelvin, no atoms are actually moving. You aren't getting any electrons that are moving in atoms. So 0 degrees Kelvin, you'd be dead. And then likewise, at 100 degrees Kelvin, you would also be equally dead. Next concept to kind of cover it would be heat capacity versus specific heat capacity. So this is a picture of the First National Tower in downtown Omaha, the tallest building currently in the state of Nebraska. And this is a glass of water. And we looked at heat capacity, which means the total amount of heat that an object can hold. The tower can hold much more heat than the glass of water. But when you look at specific heat capacity, what you do is you pull 1 gram out of the tower, 1 gram out of the glass, and then you compare those. And because water has a very unique property of being able to take a lot of energy without raising the temp very much, water actually has an incredibly high specific heat capacity. Not to taunt you, but here's a pool on a nice summer day. You can see the beautiful water here and the concrete. I think you would all agree if it's a 100-degree July day and you're at a pool, what's going to happen is the concrete is going to be really hot, and then the water is going to be relatively cool. And the reason for that is concrete has a very low specific heat capacity. Water has a particularly high one. So despite the fact they're both getting the same amount of energy, it takes much longer and more energy to heat the water up than the concrete. And consequently, the opposite approach happens at night. If any of you have ever had the luxury of swimming at night, like in a pool or in a lake or a river, what happens is that the water actually is relatively warm compared to the ground and compared to the concrete or any other surface. And the whole reason for that is that the water, because though it takes a long time to heat up, it also takes a much longer time to cool down. So water is going to stay much warmer than air or concrete or the ground when it comes to that. Another example to show this is that you're walking barefoot in some grass and you come across a manhole cover, it's 100 degrees. You do not want to step on the manhole cover, unless you're a sadist, because the manhole cover is going to be incredibly hot. It can potentially scald or burn your feet, where the grass is going to be relatively cool. And again, it has to go with specific heat capacity, that the manhole cover being metal is going to conduct much more rapidly the energy and go to a higher temperature than the grass will. So here's just a cheesy thing showing 3 items when it comes to specific heat capacity: gold, aluminum, and water. And you can see on this illusion, as we heat them up all at the same time, what's going to happen is gold's going to heat up the quickest because it has the lowest specific heat capacity. Aluminum is going to be next, followed by the water, which will be last. Okay? And again, I think it should make intuitive sense to you that metals will heat up faster. Metals conduct electricity, they conduct heat. And in our kitchens at home, every piece of pot and pan in your kitchen is metal-based, whether it's stainless steel, copper, cast iron. Again, we created these pots and pans because they're the easiest things to actually heat up. And so like what happens is that'll do that process. Okay, so moving on to this example here, what I want you guys to do in your notes is to draw a line graph showing 25 grams of ice at -15 going to water vapor at 115. So how's that process going to look with time on the x-axis and temperature on the y-axis? So go ahead and pause the video, give that a shot, and then start again. You can see the details on the next slide. Okay, so here we go. So this actually is what's going to happen with water. You're going to start at -15. It's going to rise to 0, and then it's going to flatten. Then it's going to get to a certain point, and it's going to rise again, and then it's going to flatten again for that to happen. And the whole reason why this occurs is when you're in a state, so in this case solid, as you add energy, you're going to raise the temperature. This here is going to be a state change. So in this case, we're melting. We're taking the solid ice and here and converting it to water, all water here. So what's going to happen is we're going to melt everything to make that happen. Once all the water's melted again, you're going to have this constant as temperature, as heat goes in, temperature is going to go up. And then once we get to water vapor, you're going to see the same thing again, that again, the water will start going to a gas, and then that'll happen. You guys have seen this process at your houses. Again, if you already heat water for anything, you know, one, it takes a long time to do it. And two, once water boils, you take a thermometer and place it in there, that water is going to be like at 100 degrees Celsius or 212 Fahrenheit because the boiling point of water is generally considered constant. So one big equation to work with when it comes to thermochemistry, and again, I will tell you, we're almost to the point now where every unit we cover is going to have different concepts and topics when it comes to chemistry, and then a couple equations that as long as you know what the variables are and how to rearrange and solve, so essentially basic algebra, you're going to be in great shape for the rest of the year. And this is an example of this. So this equation here, Q equals MC delta T. Q would be the number of joules. So joules is an energy unit. It's just indicating like how much energy do you have. So like you can use temperature would be like a unit or mass. Scientists have set this thing called joule for the energy unit. The bigger the number is, the more energy you get. The lower the number is, the less energy you get. And again, that number can be positive or negative depending on the situation. M is mass, we talked about before. C is specific heat capacity. And then it's important to know this one, delta T. Delta T is always going to be final temperature minus initial temperature in Celsius. You got to make sure to keep that straight because delta T will dictate whether Q is positive or negative, and that will impact you when it comes to homework, quizzes, and tests. So always put the final temperature first minus the initial temperature to get the delta T. It's not an absolute number. So I have this item here to kind of work through. Here is the specific heat capacities of water, ice, and water vapor. This is the heat of fusion going from solid to liquid or liquid to solid. It takes 6.01 kilojoules per mole. And then heat of vaporization is going from gas to liquid or liquid to gas for that. And again, when you can see this, this is very similar to the previous diagram I've shown. So you have water as ice in the state of ice here, water has liquid water here, and then water has water vapor here. So we're going to work through this problem, and I want you guys to try to give this a shot first before you look forward. But the question I have for you, what's the energy to convert 25.0 grams of ice at -15 degrees Celsius to water vapor at 115? I gave you the Q equation. I have the specific heat capacities of water in its three states, and the heat of fusion for going from solid to liquid, heat of vaporization going from liquid to gas. So I want you guys to go and pause the video and try to determine what this is, and then I'll work it out on the next slide. Okay. So moving forward, actually, let me move back real quick. So the problem I gave you on the previous slide actually has 5 parts. So you're going to use the same equation, Q equals MC delta T, for the part here as you raise the temperature on ice, for the part here as you raise the temperature on water, and for the part here as you raise the temperature of the water vapor. And then this flat part here, you're going to use the heat of fusion. This flat part here, you're going to use the heat of vaporization to make that happen. Okay, so for part one, going from ice, we have 25 grams of ice. The specific heat capacity of ice is 2.03 joules divided by grams delta C. And then the temperature change, the final temp is 0. The initial temp is negative 15. So 0 minus negative 15 gives us a temperature of 15. So when you multiply this together, everything's going to cancel with the joules. You're going to end up with 761 joules. For the second one, when you start at 0 degrees Celsius and go to 100 when it's water, we have the same amount of water for this, or it's 25.0 grams. You're going to have the specific heat capacity of water, which is 4.179. Then it's going to be 100 minus 0 to give us 100, and that's going to be 1.04 times 10 to the fourth. Last one, you're going to take 25.0 grams of water times the specific heat capacity of water vapor, which is 1.84. Then you're going to have 115 minus 100 to get us 15 degrees Celsius. Multiply that together, you're going to get 690 joules. So what I just did was this part here, and this part here. So the next thing we need to do is then do the conversion from ice to water and the conversion from water to water vapor. And for that, you're going to need to use just a basic 2T chart where the first thing you want to do is convert the grams of water to moles, because the specific heat, the heat of fusion and vaporization are given in kilojoules per mole, so you have to have the item in moles to make that occur. So what's going to happen is I'll have 25.0 grams of water. I'll divide by 18.02 grams. I'll multiply that by 6.01 kilojoules. 25 divided by this times this will give me 8.34 kilojoules. Then consequently, to figure out the kilojoules for the water vapor, of 25.0 grams of water, 1 mole is 18.02, and then we have 40.65. When you multiply that all the way through, you're going to get 56.4 kilojoules. So again, the top one here is the amount of energy to convert ice to water. And then the bottom calculation was the amount of energy to convert water to vapor. So when we do all that, and I line all that up for the heating up the ice, heating up the water vapor, these were the answers for that. For the heat of fusion, going from ice to water is this. For the heat of vaporization, water to water vapor is this. And then what we have to do is add these up. And the only last stumbling block to doing this problem is that this is in joules and this is in kilojoules, so we have to convert. The beauty, again, of metric is anything that has kilo is basically 1,000. So either you need to convert this to joules or those to kilojoules to make that work. I went ahead and converted, for this one, I converted them all to kilojoules. So 761 joules will be 0.761. The joules to kilojoules for raising up the temperature of water is 10.4. And then the amount of kilojoules for raising up water vapor from 100 to 115 is 0.69. Heat of fusion, heat of vaporization will get us 76.6 kilojoules. If you did that in joules, which again, that would be acceptable unless I indicated which way I wanted it, it would be 76,600 joules. Now, again, these numbers should make sense. If you've ever boiled water, and try this if you don't believe me, like boil water at home with a thermometer. It'd be like the boringest thing ever, but we have a pandemic going on, so we're kind of in the era of boredom. But if you ever boil water, if you take temperature readings of that water as it's heating up, you'll notice it'll rise pretty quickly to get from the temperature out of your faucet close to boiling. But then what happens is once you get it to boiling, it takes a long time to evaporate all that water, to boil off all that water. So if you look at this, like going from ice to liquid doesn't take that much work. Again, this one just took work because, one, the specific heat capacity is higher in water, and we moved it the most degrees, a full 100. But then most of the work we did, the vast majority, was basically melting the ice. And again, if you have like an ice water bath, you can have, if you have enough ice, you can actually keep a water bath close to zero for days if you have a appropriate cooler and things like that. And then obviously, boiling water is just a very intensive process. It takes a lot of time for that to happen. All right, so let's go and try this one then. So you have 4.5 grams of gold. It absorbs 285 joules. What was the final temp? And gold specific heat capacity is this. So pause the video, try to work this one out, and then I'll show the answer on the next slide. Okay. So here's the deal. I need the Q equation. I changed delta T to TF minus TI. Let's plug everything in. So the Q was provided in the problem as 285. The mass of the gold is 4.50. SHC just stands for specific heat capacity is 0.129. TF equals TF, which is what we're trying to find. TI is going to be 32.5 degrees Celsius. Let's go ahead and then do the problem here. So when I plug everything in, I'll get 285 joules. We'll have 4.50 times 0.129, TF minus 32.5. So when we set all this up here, we'll get TF minus 32.5. So we'll have 491 equals TF minus 32.5. We'll add 32.5 on both sides to get 524 will be the TF for that. So again, like previous problems we've done with the Q equation, if you have 3 out of 4, or they give you final and or initial, if you have 4 out of 5, you can solve for the unknown. So this diagram here shows 2 beakers of water. They both have the same amount of dye, but one has warm water and one has cold water. And I want you guys to pick which one you think has the cold water and which one you think has the warm water, and then I'll talk about it. Okay, so I think most of you potentially realize that this would be the one with the warm water. And the question always is, well, why does the dye move much more quickly through the warm water than the cold water? And the answer is that the water molecules are actually moving faster. So what happens is, though you can't see it, the water molecules in both of these beakers are moving. And because this one's at a higher temperature, the water molecules are moving faster. Because they're moving faster and have more collisions, you can disperse dye into it more quickly than you can in colder water that's moving slower. So again, warmer bodies have more kinetic energy, colder bodies have less kinetic energy. And kinetic energy is just how much energy does it actually have. This diagram here shows, again, faster moving, colder is slower moving. So here's this. Excuse me. So here's ice and water. And this just shows the energy. That essentially what's going to happen is there's going to be more energy in the water than there will be in the ice, which makes sense because of that. So let's move on and talk about enthalpy. So enthalpy is change in heat energy. And so what happens is if you have an endothermic reaction, that's going to have a positive enthalpy. And then that delta H actually goes on the reactant side right here. If you have an exothermic reaction, the delta H is going to be negative and it's going to go on the product side. So let me show you 2 examples of this. So here we have exothermic right here. We have C4 plus 2O2 goes to CO2 and H2O. Our delta H is negative 810 kilojoules per mole. And again, I wanted to not have to worry, does this go here or here? If it's negative, just throw it on the product side. For endothermic, Again, it's a positive delta H, and you can just throw it on the reactant side. So here's an energy diagram to show this. And these diagrams are pretty straightforward. Exothermic reactions, the products are going to be lower than the reactants are. And then the delta H is the difference between the reactant energy and the product energy right here. So what's going to happen is you're going to have some type of activation energy to make the reaction go forward. If the products is at lower energy than the reactants, it's exothermic. And then this negative 810 will be located right here. This is an endothermic reaction, so you would anticipate if you drew a diagram of an endothermic reaction, the products are going to be higher than the reactants. And so the activation energy will go here, and then delta H will again, for this time, be positive because it's absorbing energy to make that happen. And again, that's going to be the energy potential between the reactants and the products right here. So to put this into terms with equations, we have this problem here. If you start with 56.0 grams of nitrogen gas with unlimited oxygen gas, how much energy will this endothermic reaction need? So go and pause the video and try to give this a shot. I have the answer on the next slide. Okay, so here we go. So I have 56.0 grams of nitrogen gas. So it's going to go on my T-chart in the upper left like always. I need to convert it to moles because we always convert grams to moles when we're working with stoichiometry. So 1 mole of nitrogen is going to be 28.02 grams. Then the only difference is what we've done before is you're still going to go to the balanced equation to move things. But unlike before where we moved from one item to another item, the item we're going to move to is delta H. So when you look at this, we have 1 mole of N2. We'll put here because we're going away from nitrogen. And I want to know the delta H. So I'm going to put 1 mole of delta H on top right here. Then what's going to happen is when I look at my delta H is a positive 181. So 1 mole of delta H is going to be 181 kilojoules. So I can cancel grams, cancel moles of delta H, and then I will end up with kilojoules. When you multiply and divide that through, you're going to get 362 kilojoules for that. Here's another practice problem. If you start with 100 grams of hydrogen peroxide, how many moles of oxygen will be given off? This should be a review on what we've done before, so I'm going to pause the video and try this one. So this one, we're just going grams to moles. So grams of hydrogen peroxide was 100. The molar mass of hydrogen peroxide is 34.02. We have 1 mole to 2, and that'll get us 1.470 moles of oxygen to make that work. And then for this one here, I want to know if I start with 100.0 grams of hydrogen peroxide, how much energy will be given off. So what's going to occur, so go and pause the video and give this one a shot, and then I'll work it out on the next slide. So what's going to happen is very similar to the previous one I showed you. We need to convert to moles. This is the molar mass of hydrogen peroxide. For the balanced equation, we're going to delta H, but we're coming away from 2 moles of hydrogen peroxide. The delta H is negative 196. So when we multiply that through, we're going to get negative 288 kilojoules. So as long as you can do these practice problems here, and I have another video over that, you're probably going to be in good shape for most of this unit. Again, energy diagrams are real when it comes to real life. So this is an energy diagram here of this reaction. It is exothermic because the reactants are higher than the products. So the products are lower at the end. And then the delta H for this would be the difference between the products and reactants, which in this case will get us negative 850 kilojoules per mole. Then what's going to happen here with this process is that the delta H with this reaction will be here. That'll be a positive delta H of 365. So let's go ahead and do Hess's law real quick. So Hess's law allows you to get an answer indirectly. So essentially, there's a series of equations, and we know how much energy these equations have. But instead of every single equation out there, we gave the most common ones, and then you can kind of place them together. So the 3 rules for Hess's law are this. Rule number 1, if you flip the equation, you got to flip the delta H sign. Rule number 2, if you multiply or divide an equation, multiply or divide the delta H. And rule number 3, if several equations are added up, you add up all the delta H's. So for any delta H equation, I'm going to have an equation that I want. This is my goal. And then I have to give you the half reactions to make that goal work. So you're going to manipulate these two bottom equations here until you get this equation here, and then that'll help us get the delta H. So I labeled them in colors red and purple. So for the red one here, I need 2 sulfurs, so I multiply everything by 2 to get that. So the equation going into this will be this. Then for the purple one, I will need the SO3 on the product side, so I'm going to flip it. And then when I flip it, what's going to happen is that it's going to change the sign. And then on this one here, I just need to add it together. So when I add it together to get the delta H, you're going to cross off things that are similar. So 2 SO2s are similar. We have 2 oxygens and 1 oxygen to get us 3. So we're left with 2 sulfurs, 3 oxygens, and 2 SO3s. And then when we add a negative 594 plus a negative 198, we get a negative 792 kilojoules, which will then be our answer for that. This one here is a little bit more challenging. So going to pause the video and try to give this one a shot. And again, this is your goal equation. So rearrange these equations here to achieve this goal. So pause the video, give that a shot. Answers on the next slide. Okay. So when you rearrange everything, you should get negative 906 kilojoules per mole. That one I'll probably work out together in class next time I see you guys and we talk about this item. So that's it for thermochemistry. Again, I covered the concept, I covered the Q, we covered Hess's law. You guys should be okay for that. And again, as always, I'll take questions. We'll work through this in multiple ways to ensure that there's clarity and you guys can be successful on the assessment pieces. All right, that's all I got for today.